Some ad hoc methods, the methods of bounded search tree and the problem kernel. The method of bounded search trees, the basic method. The method of bounded search trees is probably the easiest to apply and is based on the following facts. Many combinatorial problems can be solved by algorithms that can be decomposed into two distinct parts. First, within the algorithm, we compute, perhaps inefficiently, some search space which is often an exponential-sized search tree. Thereafter, we run some relative efficient algorithm on each branch of the tree, often simply based upon, say, depth-first search. The exponential worst-case complexity of such algorithms comes from problem instances where we need a complete tree traversal. Many probabilistic analyses for such problems are based upon how often significant tree traversal is needed. For our purposes, the critical observation is that for many parameterized problems, the size of the tree depends only upon the parameter. Then, for a fixed k, the search space becomes constant size, and the algorithm is then efficient for each fixed k. A classic case of the application of this technique is the vertex cover problem, problem 2.1 of chapter 2. The reader should recall that the vertex cover problem takes a given graph G and asks if there is a size k set of vertices that cover all the edges. Theorem 3.1. Downey and Fellows. Vertex cover is solvable in time big O of 2 to the k times the size of V of G, where the hidden constant is independent of k and the size of V of G. Proof. We construct a binary search tree of height k as follows. Label the roots of the tree with the empty set and the graph G. Choose an edge U, V in E. In any vertex cover V prime of G, we must have either U is in V prime or V is in V prime. So we create children of the root node corresponding to these two possibilities. Thus, the first child is labeled with U and G minus U, and the second child is labeled with V and G minus V. The set of vertices labeling a node represents a possible vertex cover, and the graph labeling of the node represents what remains to be covered in G. In general, for a node labeled with the set of vertices S and the subgraph H of G, we choose an edge UV in E of H and create the two child nodes labeled respectively S union the set of U and H minus U, and S union the set of V and H minus V. If we create a node at height at most k in the tree that is labeled with a graph having no edges, then a vertex cover of cardinality at most k has been found. There is no need to explore the tree beyond height k. Convention. Henceforth, we will omit the phase where the hidden constant is independent of k and G, since it will be obvious and implicit. The hidden constants will always be small. In passing, we remark that the proof of Theorem 3.1 above also establishes the following result. Corollary 3.2. The problem log vertex cover, which asks if a given graph G has a vertex cover of size less than equals to the log of the size of G, is in P and is solvable in time big O of the size of G to the second, the square. Corollary 3.2 improves the work of Papadimitriou and Yannakakis. We will look at the relationship of our work with that of Papadimitriou and Yannakakis in Part 3. The vertex cover problem asks us to consider the size of sets where vertices cover edges. A well-known related problem is that of dominating set. In dominating set, vertices cover vertices. Dominating set input, a graph G, parameter, a positive integer k. Question: does G have a dominating set of size k? The dominating set is a set V prime, which is a subset equals to V of G, where for each U in V of G, there is a little v in capital V prime, such that UV is in E of G. In Part 2, we will examine evidence that despite its apparent similarity to vertex cover, dominating set is not fixed parameter tractable. However, using the method of bounded search trees, it is possible to prove that several interesting variations of the dominating set problem are FPT. A nice example of an FPT variation of the basic dominating set problem is provided by planar dominating set, which is the restriction of dominating set to planar graphs. We will need the following lemma. Lemma 3.3, if G equals to VE is a simple planar graph with a vertex partition into two sets V equals to V1 union V2, satisfying 1. The minimum degree of vertices in V1 is at least 3. 2. V1 is an independent set in G. Then there is a vertex U in V2 of degree at most 10 in G. Proof. Let G be a counterexample of a minimal possible order having maximum number of edges. And consider an embedding of G in the plane. Let H denote the subgraph of A of G induced by V2. In any phase of the inherited embedding of G, there can be at most one vertex of V1, else an edge could be added between two vertices of V2 on the boundary of the phase, and therefore G would not have a maximum number of edges as supposed. Let U be a vertex of degree at most 5 in H. The vertex U is on the boundary of at most 5 faces of H, and consequently in G, U has degree at most 10. Theorem 3.4. Downing and follows. Planar dominating set is solvable in time big O of 11 to the k times the size of G. We construct a search tree for which each node has at most 11 children. Each node in the tree is labeled with a set of vertices S that represent a partially constructed dominating set. The root node labeled with the empty set will have at most 6 children based on the following consideration. Since G is planar, G has a vertex V of degree at most 5 which can be found in linear time. Any dominating set for G must contain either V or one of the neighbors of V. We create a child node for each possible choice of a vertex to dominate V. In general, for a node in a search tree, we first check whether S is a dominating set. This can be done in linear time. The levels of the tree correspond to the cardinality of the labels S, so the tree will have height at most k. To compute the children of the node, we find a vertex U in G not dominated by S that has degree at most 10 and create a child node for each possible choice y of a vertex to dominate U. There can be at most 11 possibilities, including U. The child node is labeled with S union the set of Y. We must argue that such a vertex U must be available. This being so, it can be easily be found in linear time. We term such a vertex U a splitter for the node in the search tree. Let capital U denote the set of vertices not dominated by S, and let T equals to V minus S minus U be the set of vertices not in S and not in U. Let H be the subgraph of G induced by V minus S, which is equals to T union capital U, and let H prime be the subgraph of H obtained by deleting from H any edges between vertices of T. Observe that a set of vertices W, which is a subset equals to V minus S, has the property that S union W is a dominating set in G if and only if W is a dominating set in H prime. In other words, we may restrict our attention to H prime in searching for a splitter. H prime satisfies condition 2 of lemma 3.3, but there may be vertices in T that have degree 2 in H prime. Necessarily, any such vertex R in T of degree 2 has two neighbors ST in U. Consider the graph H prime prime obtained from H prime by deleting such vertices R and adding the edges ST. Lemma 3.3 applies to H prime prime, so there is a vertex U in capital U in H prime prime of degree at most 10. The splitter vertex U also has degree at most 10 in H prime, H, and G. As our last example of the technique of bounded search trees, we consider the parameterized version of a classical problem in Gary and Johnson. Feedback vertex set. Instance, a graph G equals to VE, parameter, a positive integer K. Question, is there a set of vertices V prime which is a subset equals to V of cardinality at most K such that G minus V prime is a cyclic? Theorem 3.5, feedback vertex set is solvable in time. Big O of 2k plus 1 to the k times n squared. We will need the following lemma. Lemma 3.6. There is an big O of size of G to the square algorithm for the problem almost minimum below. Almost minimum. Input a graph G, output infinity if there is no cycle in G. Otherwise, output a cycle of length less than equals to m plus 1. Here m is the length of the shortest cycle in G. Proof, the algorithm runs as follows. Let G equals to VE for each x in V. Let almost of x be the algorithm below. Algorithm 3.7, almost of x. Step 1. Declare that x has level x equals to 0. Set k of x equals to infinity. Step I plus 1. Using, say, a cube, examine the vertices at level I in order. This is breadth first. For each such vertex x prime at level I, consider the set of neighbors of x prime not at level I minus 1. Suppose that we are considering V, a neighbor of a vertex x prime at level I. It will be the case that V has no level, and we declare that V has level I plus 1. Now see if there is any vertex Q not equals to x prime either at level I or already at level I plus 1 by the time we consider V, and such that V is adjacent to Q. If such a Q exists, then terminate the algorithm and return k of x equals to I. If we consider all of level I plus 1 and find no pair VQ, then move to step I plus 2 until there are no vertices without a level. For each x in V, almost of x takes big O of size of V many steps. Let k mean equals to the minima of the set of k of x such that x is in V. The claim is that if k of x is equals to k mean, then x belongs to a minimum circuit of G. To establish the claim, suppose that W is a vertex that belongs to a minimum circuit. If M is even, then almost of W stops when a vertex W prime is found at level I plus 1, completing a cycle at level I, and k of W equals to M over 2 minus 1. See figure 3.2, even case. If M is odd, then we can either find W prime completing a cycle at level I or completing a cycle at level I plus 1, as we see in the two odd cases of figure 3.2. In the odd case, k of V is less than or equals to M minus 1 over 2. Thus, almost of V finds a cycle that is no longer than 2 times k mean plus 2 and hence no longer than M plus 1. It is clear that the cycle contains W. Thus, for each x in V, we compute k of x. From the collection of k of x, we compute k mean, and then we are able to compute an almost minimal cycle for G. The cost is the cost of calling almost of x times the size of V many times. This is big O of the size of V to the square. As Itai and Rhoda observe, if we have some guarantee that the minimum cycle is of even length, then the algorithm above will return a minimum cycle. This observation applies to the case that G is bipartite. Proof of Theorem 3.5. First, note that a graph G has a feedback vertex set of size k if and only if the reduced graph G prime has one, where G prime is obtained from G by replacing each maximal path in G having internal vertices O of degree 2 with a single edge. Note that the reduced graph G prime may have loops and multiple edges, but that if G prime is simple, then it has minimum degree 3. The reduced graph G prime can be computed from G in linear time. Also in linear time, a k-element feedback vertex set that has been identified in G prime can be lifted to a k-element feedback vertex set in G. As in the proofs of the theorems above, we build a search tree where each node is labeled with a set of vertices S representing a possible partial solution. The cardinality of a label corresponds to the height of the node in the tree, and we will therefore explore the tree to a height of no more than k. In linear time, we can check whether a set S is a solution. If the labeled set S of a node in the search tree is not a solution, and the node has height less than k, then we can generate the children of the node as follows. Let H denote the graph G minus S, and let H prime be the reduction of H, as described above. If a vertex V of the H prime has self-loop, then V must belong to every feedback vertex set of H prime. Corresponding to this observation, we create a single child node with label S union the set of V. If the reduced graph H prime of the graph H equals to G minus S has multiple edges between a pair of vertices UV in V of H, then either U of V or V must belong to every feedback vertex set of H prime, and we correspondingly create two child nodes with labels, respectively, S union U and S union V. If the reduced graph H prime has no loops or multiple edges, then we can make use of the following claim. If a simple graph J of minima degree 3 has a k-element feedback vertex set, then the girth of J, the length of a shortest cycle, is bounded above by 2k. We prove the claim by induction on K. If J is simple, then by a standard result, J must contain a subdivision of K4, and this implies that a feedback vertex set must contain at least two elements. For the induction step, suppose U prime is a feedback vertex set consisting of k plus 1 vertices of J. Suppose that UV in capital U prime with the distance from U to V, d of UV is less than or equals to 2 in J. Contracting the edges of a shortest path from U to V yields a graph J prime of minima degree 3 that has a feedback vertex set of k elements. By the induction hypothesis, there is a cycle C in J prime of length at most 2k. This implies that there is a cycle in J of length at most 2k plus 2. Otherwise, suppose no two vertices U and V of U prime, capital U prime, has d of UV is less than or equals to 2 in J. Then every vertex of J minus U prime has degree at least 2. So there is a cycle in J not containing any vertex of U prime, a contradiction. This establishes our claim. By the above claim, we note that for the node of the search tree that we are processing, either H prime contains a cycle of length at most 2L, where L equals to k minus the size of S, or S cannot be extended to a k-element feedback vertex set. The algorithm of Itai and Roda from lemma 3.6 can be employed to find in H prime a cycle of length 2L or 2L plus 1 in time big O of n squared. Thus, in time big O of n squared, we can either decide that a node should be a leaf or of the search tree because there is no cycle in H prime of length at most 2L plus 1, or we can find a short cycle and create at most 2L plus 1 children, observing that at least one vertex of the short cycle that we discover in H prime must belong to any feedback vertex set. As we will see in Chapter 8, feedback vertex set can be shown to be solvable in time big O of the size of G. Downing and Fellows, both lambda, the running time is big O of 17 times k to the 4th times the size of G. It is unknown if the directed version of a feedback vertex set is in FPT.